Good morning, everybody. In the electron devices and circuit theory subject, today let us see about the Zener diode. Here we will be seeing about the diode, how the diode is working, what are the basic principles of the diode, and what are the applications of the diode. So here you can see the symbolic representation of a Zener diode. Okay. So it is having two terminals. Okay, so this is Zener diode is a normal PN junction diode, but it will be heavily doped. The doping level will be very heavy in the case of the PN junction this one Zener diode. So if it is a normally doped or moderately doped P and both P and N region which are connected together, which forms a diode, the same case only here for the Zener diode, it is a heavily doped PN junction diode. Okay, so heavily doped PN junction diode. So under normal condition, that is under forward bias, when your anode is connected to positive terminal and cathode is connected to the negative terminal of your external supply, your Zener diode will also act as a normal PN junction diode. Okay. So under reverse bias condition, means what? Your anode will be connected to negative terminal. Here your anode will be connected to negative terminal, and your cathode will be connected to the positive terminal. This is the case you are connecting the reverse bias condition. So when you are having the reverse bias condition, what will happen in your norm? You will see how the Zener diode is acting. Okay, so in your normal, so normally in case of PN junction diode, the breakdown occurs in a PN junction is because of the avalanche breakdown. Okay, so because of avalanche breakdown, AVALANCHE, so avalanche breakdown. But in the case of the Zener diode, the breakdown occurs because of the Zener breakdown. So avalanche multiplication is taking place in the case of the normal PN junction diode, but here it is because of the Zener breakdown. How it happens now? Since it is heavily doped PN junction diode, the P region and the N region are heavily doped. So normally in near the depletion layer, you will be having a electric field, will be a small electric field will be generated in the near the depletion region. So because of that electric field, your immobile ions, the covalent bond breaks down by itself. The covalent bond breaks down and it will become a mobile electron hole pairs. Okay, so once we are having a mobile electron hole pairs, it will go and collide with the other covalent bond. Again the electron hole pairs will be generated. So your Zener current will starts to flow. This is how Zener breakdown happens. So under reverse bias condition, here the breakdown will be occurring. So here you can see. So this is for the characteristics of the Zener diode. This is for the forward bias characteristics. So here you can see in forward bias characteristics. What about here? In forward bias characteristics, you have this one. This is acting in the no, it is acting as a normal PN junction diode. Okay, so under reverse bias condition, so breakdown region is normal operating region for Zener. So once this breakdown occurs before, that is, if a normal PN junction diode, the breakdown is occurring here, means in Zener the breakdown is occurring before that, that is at lower voltage itself the breakdown will occurs. Okay, the voltage at which the breakdown occurs is termed to be the zero voltage, and the current which is flowing will be start to increase drastically, and the current is termed to be Zener current. Okay, and this one the Zener current or knee current. Okay, so this is the maximum Zener current. Beyond that, if you are increasing your diodes, means your diode will be getting damaged. Okay, so the same as the reverse voltage, when you are increasing the VR voltage, the reverse current extremely small up to the knee voltage. So after that after the reverse current, and the current which is flowing is termed to be the Zener current. Okay, So once the breakdown occurs, once the breakdown is occurring, after that the current will start to increase drastically, and the current voltage will be remaining constant. It is the case, the voltage will be remaining constant. Okay, and the Zener internal resistance. So what about this? So Zener resistance, it is the slope, it is taken from the slope of the curve of VA characteristics. Okay, and when we come to the application, so what we have observed here, the the voltage is remaining constant. So Zener diode can be used as a voltage regulator for providing stable reference voltage. It is used in many switched mode power supplies, regulated power supplies, and wherever we require a constant voltage irrespective of your load and voltage regulation, you will be going for the Zener diode. Okay, so it is major application. It is the Zener diode. The operation, the major operation will be in the reverse bias region. Okay, in the reverse bias region will be acting. So here you can see, so this can be replaced by, this can be replaced by a voltage source. So this is the equivalent circuit. So after here you can see, so this is the breakdown voltage where it is occurring. After that, even though there is the increase in the current, your voltage is remaining constant. Okay, but in practical cases it cannot be represented by a single model. We'll be having a Zener impedance also, and your slope will also be like this, and your Zener impedance can be represented by, as I have explained, Zener impedance can be represented by slope of the curve. So it can be represented by delta of Vz by I Z. Okay, so here you can see first case, you are increasing, what you are doing, you are increasing, the input voltage is increasing, but what about here, your Zener voltage will be remaining constant. Okay, so this is the first case. Second, even though your input voltage is decreasing, your output voltage is also remaining constant. That is why the major application of the Zener diode is used in the voltage regulators. Okay, thank you all.